Hello everyone. Today we are going to discuss about our last chapter, state variable analysis in control systems. Right? Okay. Now, what is state variable analysis? Why it is important in control systems? So these are the contents we will discuss in this chapter. Concept of state variable analysis, different forms of state variable representation, concept of diagonalization, obtaining state equations from transfer function representation and vice versa, solution of state equations, that again state transition matrix, methods of finding state transition matrix, so that is power series method, Laplace transform method, Cayley-Hamilton method, and finally controllability, observability of linear systems, and also testing of controllability and observability by Kalman's test. Okay, so these are the contents. Now we'll start with the introduction. State variable analysis. It is a powerful tool, or you can say powerful technique, or it is an excellent method for the design and analysis of control systems. The best method you can say in the design and analysis of control system. The design and analysis of the following systems can be carried using the state space methods. Linear system, it is applicable to linear system, or it is also used in nonlinear systems. It can be applied for the time invariant as well as time variant systems, and also it can be applied to multi-input multi-output systems. Okay, the old one, you can say old and conventional method for the design and analysis of control system is transfer function method. So transfer function method, because last few videos we have discussed based on the transfer function method only. So those methods, they have some drawbacks. Okay. Now we will discuss about what are the comparison between state variable approach and transfer function approach. Transfer function approach, it is a frequency domain, and state space or state variable method, it is a time domain approach. Transfer function, it is unique, but state model, it is not unique. In the transfer function, we are taking only input, output, and error signals are important, and are physical variable and also measurable. But in the state space, chosen state variables need not represent physical or measurable variables. Okay. Design methods in the transfer function method are trial and error approaches and are approximate only. But in the state variable analysis, there is no trial and error method. Systems can be designed optimally. Okay. Transfer function can handle only linear and time invariant systems only. And state variable approach or state variable analysis also handles nonlinear and time varying systems, because it can be applied to linear as well as nonlinear, and also time invariant and also varying systems. And generally, it is a limited transfer function method limited to single input, single output systems. Multi-input, multi-output systems are difficult by using transfer function approach. But in the case of state space analysis, it is very easy to handle both single input, single output, and also multi-input, multi-output systems. In the transfer function approach, initial conditions are neglected, but in state space analysis, initial conditions also considered. In the transfer function approach, internal variables cannot feed back, but in the state space analysis, internal variables can be fed back. In the transfer function approach, it requires Laplace transform for continuous signal If it is a discontinuous, or you can say discrete signals, it requires Z transforms. But in state space, that is, it treats both similarly, same way only. Okay. Transfer function models can be handled by manual methods. Computational intensive and often needs use of computers. Nowadays, both the measures we are using, that is the simulation methods, we are using MATLAB and other free open source softwares also in use, and you can find the transfer functions. But particularly in transfer function models can be handled by manual different methods we are using. Okay, these are the comparisons between transfer function methods and state variable analysis, state space methods also. Okay. Next, we will take some definitions and some terms we are using in the state space analysis. First one, state. What do you mean by state? Generally, the state of a dynamic system is the smaller set of variables. It is called state variable. Okay, the smaller set of variables are called state variable. So that the knowledge of these variables at t equal to t0 together with the knowledge of input for t is greater than or equal to t0 determine the behavior of system for any time t is greater than or equal to t0. That means the knowledge of a particular variables at t equal to 0, t equal to t0 with the knowledge of input determine the complete the behavior of the system for any time, that is t is greater than t0. Okay, so that particular state you can say here it is at that time you can find out any with the knowledge of input and the variables, state variables. That is called state. State variables. The state variables of a dynamic system are the variables making up the smallest set of variables that determines the state of the dynamic system. Basically, the state variables are smallest set of variables that determines the particular state of dynamic system. Those are called state variables. State vector. If n state variables are needed to describe the behavior of the system, then n state variables can be considered n components of a vector x. Such vector is called state vector. Simply, whatever the state variables we are representing in terms of vector, it is called state vector. Okay. State space. The n-dimensional space whose coordinates or axis consists of x-axis, x1, axis, x2 axis and so on, xn axis, where x1, x2 and so on, xn are state variables is called state space. That means these x1, x2 state variable axes are representing in the coordinates, that is called state space. State space equations. In state space analysis, we are concerned with the three types of variables that are involved in the modeling of dynamic systems. Those are input variables, output variables, and state variables. Okay, these are the basic definitions and terms used in the state variable analysis. Okay. Now, state variables of a dynamic system. Already we have discussed about what do you mean by state variables, right? The state of a system is a set of variables such that a knowledge of these variables and input functions will, with the equations describing the systems, dynamics of the systems, provide the future state and output of a system. For a dynamic system, if you see this one black diagram, you can say right hand side these are the output signals and the left hand side these are the input signals, and the state of the system is described in terms of set of state variables. Those are the state variables x1, x2. Okay, the state variables describe the future response of the system given the present state and excitation inputs and equations describing the dynamics of the particular system. Okay, So simply you are saying state variables describing the dynamics of the system. If you take the state differential equation, whatever the state variables are representing in terms of the first order differential equations, this is the main advantage of this. Whatever the equations you are taking are simply converting nth order differential equation is converting into first order differential equations. Okay, let us see here. These are the x1, x2 and so on, xn. These are the state variables. And the next equations, these are the first order differential equations in terms of state variables. So x1 dot means here it is a first derivative dx1 by dt, and second one dx2 by dt and dxn by dt, right? This is the first order only. So these equations, simply you can say algebraic equations only here. So we are representing in terms of first order differential equations. So these equations are representing in terms of standard form. So that is d by dt of x. X is a state vector. So it consists of state variables x1 to xn. Okay. Simply you can say here, you can write this one, it is equal to x dot. That is equal to matrix, these coefficients A into x. X is again it is a state vector plus these are the B coefficients B11 to B1m and so on Bnm into matrix U. You can say here it consists of U1 to U. So in general we can take x dot equal to Ax plus Bu. Ax plus Bu. Okay. Similarly, the output expression it is y equal to Cx plus du. This is the state equation and this one it is output equation, right? So where A, B, C, D, these are the matrices. U is the input, Y is the output and X is the state variable, state vector. Okay. And A is a system matrix, B is an input matrix, C is the output matrix and D is the direct transition or direct transmission matrix. Okay. In the next class, we will discuss about the state model. That is, it consists of state equation and output equation. I will explain in the next video. Okay. Thank you.